just turbine. So gas turbine system, again compressor, shaft and turbine. Okay, so here you are taking power, compressor, turbine, combustion chamber. We discussed compressor, combustion chamber, now turbine. So turbine blades are very important because it will be facing very high temperature. Okay, so your material is very important here. Okay, let's say my turbine. So here you can see these are actually airfoil shaped. Okay, so this, if this is my stator, this fluid, if I put, this is separated. Now if I make it closer, so this angle will be hitting this one, hit this surface. Okay, and your turbine blade will be rotating. Fine. So turbine blade shaft, it will be fixed with shaft. Okay, and this one will be fixed with your casing, so non-rotating part. Now stator, if I draw same way, stator blades are like this. Top view I am seeing. I am not drawing any other part, only same top part of airfoil. Okay. Now fluid is going like this. Now you see the turbine blade. Turbine blade is like this, right? So stator, rotor, then rotor. After rotor blade, velocity direction is like this, right? Then again I must have one stator, same way as compressor. Okay, then stator will be giving again angle, my rotor will be having another. Okay, so that way 1 stage, 2 stage, 3 stage you can harness energy. The same way compressor, turbine, basic principle same. Rotor, stator will be constituting 1 stage, and stator will not harness or will not give any energy. Rotor will be harnessing only energy. Okay, and it will be facing very high temperature. So material consideration is very important for turbine, rotor, especially rotor blade, because stator is not rotating. So because of centrifugal force, something will be happening, chance is less, but rotor is rotating, so there is one centrifugal force and vibration there, plus high temperature. So material creep is one important parameter, creep. Okay, so creep means at long time, if it is facing that high temperature, what will happen, permanent deformation of blade is possible. So at high temperature, centrifugal force is there and it is harnessing energy also, so extra force is there, again temperature is high. So in that case, blade material can be changed permanently, that shape or size will be modified. So that will be a harmful for turbine system. Okay, it may be harnessing less energy, or it may fail continuously. It may fail because of its rotation. And if it is failing means, like for example aircraft, one blade is broken means whole thing gone, right? So everything must be safe. So material research and vibration analysis, all the things must be done when you are designing a gas turbine system. Okay, so velocity, if I draw in a rotor blade, like I have stator, rotor, stator, rotor. Okay, then velocity, pressure will be like little bit drawing down. So every time pressure will be down actually, and your velocity in stator, velocity will be increasing, again rotor will be taking velocity, again it will be increasing, again decreasing. So that way stator, when it is guiding, sometimes it will create increasing velocity. Okay, and rotor, again it will be extracting energy, so velocity will be down, but pressure continuously be going down. When pressure is down, so your fluid is actually expanding. Fluid expanding means your turbine, when you are drawing, it must be expanding actually, right? So turbine drawing will be like this, shaft is here, so stator, rotor, so gradually expanding. Okay, gas turbine will have one compressor system. Compressor will be connected to a turbine, and there will be one combustor or combustion chamber, fluid entering, exiting, it is going out. Okay, if I plot in TS diagram, it will be looking like this. Okay, 1 to 2, 2 to 3, 3 to 4 is the flow path. So in TS diagram, if you plot it, it will be like this: 1 to 2, we are assuming this is isentropic process. 2 to 3 heat addition process, constant pressure 2 to 3, and 3 to 4 is your turbine. So turbine also I am assuming this is isentropic process. But if I assume actual cycle, so in that case actually your figure will be like this, 2s and 3s. So actual cycle will give less power, but in ideal cycle we will calculate more power. So that one also you can calculate if you know the values at different points. And turbine blade will have guide vane and stator. So guide vane will be guiding the fluid flow, and it will be giving to turbine blade or rotating blade. Rotating blade will be harnessing energy, or it will be extracting energy from the moving fluid. So turbine blade. So turbine blade will be failing normally because of your temperature. At high temperature, it will have failure because of creep, blade creep. Creep means like permanent deformation of blade material. So if we have very high temperature and high stress also, the blade material can be deformed. Because of that, your turbine can fail or it will be giving less power output. So to avoid creep, we have to select material such a way that at high temperature it will not be affected so much. And so we need a blade cooling arrangement. Blade cooling arrangement means like we must have certain arrangement so that temperature can be limited within certain limit. Okay, so several types of turbine blade materials will be available, and you can go to the book also. Single crystal material normally it will be used to avoid creep. So creep is a very important parameter for turbine blade. So you should remember the definition and what is the effect on turbine blade, you should remember. So enhancing gas turbine blade performance under high temperature. So if it is operating a very high temperature, then single crystal or superalloy specific material you can use, or sometimes they will be using thermal barrier coating. So thermal barrier coating actually it will not allow the higher temperature gases to give heat to actual material. Okay, so that coating will be preventing little bit, but not absolutely. Very high temperature difference it cannot maintain, but certain amount of temperature it can maintain difference. Okay, so bond coating and different types of coating will be there. Nickel based superalloys also can be used for turbine blade material, uh, because because it is working under high temperature, and that temperature, gas temperature, may be more than the melting point of the blade. So that's why this is very important part to consider coating or cooling or specific material of the turbine blade. Turbine blade cooling. So because turbine blade is facing very high temperature, so turbine blade must be cooled also. So how you are cooling? So you have one blade. Okay, I'm drawing one blade here. Let's say assume this one blade. Okay, and fluid will be going through this, through the passage. Passage means like turbine blade is here, for example, and in between the space between the blade, this is called passage. Okay, so the passage will have a very high temperature, and that high temperature fluid is touching the blade surface. Now how to reduce the surface temperature, especially surface temperature, very important. So what will they do? They'll be putting lots of holes, internal holes. Okay, and they'll be, this hole will be passing through from bottom to top. Okay, so when you are pushing very high pressure fluid or low temperature fluid, low temperature air or any gas, you are passing through, so the turbine blade temperature will be reduced. Okay, that is the purpose of turbine blade cooling. So sometime through hole from bottom to top, or sometime there will be hole around this also, so that you can maintain temperature within certain limit. If you are not maintaining temperature, temperature will be shooting up, and that will be detrimental to your system. Okay, if you see the picture also, this is the turbine blade. Okay, and turbine blade have multiple holes here or multiple holes here. Okay, and fluid will be going through this from bottom. Okay, and this portion is shown like turbine blade will be fixed on hub. So hub means like you have one shaft hole, and this portion, one extra material is here, so blade will be fixed here. So this is called hub. Okay, and hub and turbine blade, there will be some fixing arrangement. So blade you can replace and you can fix quickly also, that's why this specific arrangement is there. Okay, this is called root. So blade will be fixed on root, and when hub rotating, because of shaft rotating, it will be, everything will be rotating together. Okay. And when you're going for blade cooling, so there are lots of research going on blade cooling channel. These are called flow channels. Okay, flow channel means let's say I have one flow path like this. Okay, so flow path, if you have smooth channel, then it will have less turbulence. Less turbulence means less heat transfer. Less turbulence means lower heat transfer. Low heat transfer. Okay, now if I want to increase heat transfer rate, I can increase turbulence inside the flow channels. Okay, so how can you increase turbulence? So I can put some barrier like this. Okay, when fluid will be moving like this, they will be getting disturbed, they will be creating turbulence here and there. Okay, lots of turbulence will be created. When flow channel is having lots of turbulence, it will be creating lots of heat, it will be increasing heat transfer rate. Okay, and if you have only smooth surface, heat transfer rate will be lower, but you are putting some extra arrangement, roughening surface, or you can disturbing the flow. Okay, when you are disturbing the flow, it will create turbulent flow. And if you are not disturbing, smooth channel is there, it will be creating laminar layer will be there, laminar layer will be there. So laminar layer actually it will be preventing turbulent heat transfer. Okay, so if you can break that laminar layer, for example, the surface is here. Normally I will have laminar layer, you can remember, like this. Now if I put one bump here, so what will happen, this laminar layer will be get broken. When it is getting broken, the cold temperature air, so that will be touching metal surface. But if you have laminar layer will not allow to touch the main fluid stream on the metal surface. If you create turbulence, then what will happen, that main stream will be touching the surface, again it will be increasing turbulent heat transfer rate. Okay, it will be increasing more mixing, so increasing mixing and increasing heat transfer rate, HT, if turbulence increase. Okay, so turbulence increasing method one will be like there surface, upper surface, lower surface is there, or pipes surface is there. You put lots of pins or fin or any turbulator, or you can create dimple channel like this. Surface is here, you can create cavity. Okay, so what will happen, fluid is coming, it instead of creating laminar boundary layer, it will get disturbed here, it will create lots of turbulence here, it will be going out, again it will create turbulence, it will again create turbulence. So you are promoting turbulence because of cavitating or creating cavity or dimple surface. Or you can create protrusion surface like this, this also will create turbulence. Okay, so there are several methods, people are doing research on this one, how to improve heat transfer rate in turbine blade system, because turbine blade surface temperature is very important for its life. For example, aircraft engine, it is running for several years, right, so without any problem, so there small problem not allowed, right, whole disaster can happen. So in that's why the lots of people are doing research on how to limit the maximum peak temperature on the blade surface. Now I am giving one example here. This is General Electric uh, one gas turbine engine, which is used for marine application. So this power output 46 megawatt. This is kilowatt. So for 46.123 megawatt. Okay, so many different different types of engines are there. So here they have given two type of gas turbine system, 146 megawatt power, 152 megawatt power, and you can see this how much heat transfer rate is happening, specific fuel consumption. Okay, SFC means specific fuel consumption, so how much fuel it is taking, exhaust gas flow, you can see exhaust gas temperature is given, you see 546 degrees centigrade. Okay, about 500 degree centigrade temperature is there, exhaust gas temperature. That means turbine is facing much higher temperature. This exhaust means after turbine has taken power, that means temperature has reduced already. This means turbine is facing much higher temperature. Okay, so and RPM of the turbine, that main shaft of the turbine is 3600 or 3800, within that range. Okay, based on this maybe electrical frequency they have set this one. Again, the power output will be based on your ambient temperature. Ambient temperature is increasing, your actually performance will be dropping. Why dropping? Because gas turbine engine, the compressor is taking atmospheric air. So atmospheric pressure, atmospheric air temperature, inlet temperature is very high, then in that case actually your performance will be dropping. Okay, you can remember the Carnot cycle formula. So inlet temperature and maximum temperature, right, the ratio. So inlet temperature is increasing, your performance is dropping. So this curve is saying like that. Okay, ambient temperature increasing, so your performance is dropping. Okay, here this engine is having 42% thermal efficiency, but actually the total efficiency will be lower because this is saying only thermal efficiency, but whole system efficiency, if you see, like there will be lots of losses in bearings and here and there, then performance will be much lower. So you cannot get more than 42% actually, because if you include other losses. So another term is there, micro gas turbine. Micro gas turbine actually very small turbine, like few hundred kilowatt, 30 kilowatt to 200 kilowatt power, about that range is called micro gas turbine. Micro does not mean this millimeter or micrometer. This is micro means like kilowatt level power output, but normal gas turbine will have megawatt level power output. Okay, so that's why they are saying micro gas turbine. So micro gas turbine sometimes they will be using for combined heat and power production cases. You have excess energy somewhere, you can use this type of turbine and you can harness some energy. Okay, so combined heat and power system, there you can use MGT or micro gas turbine. Lots of aerospace applications also, marine applications also there for using micro gas turbine. So these are smaller turbine. So micro does not mean it's a millimeter or micrometer level thing. Micro means like kilowatt level power, normally 1 or 2 megawatt also maximum possible. But normal gas turbine will have several, like 46 megawatt. I have shown already one example. Okay, so thank you very much for this lecture. So I'll start new topic. Thank you.